okay? So just to review this is the receptors acting as the channel here. Very simply, we open up this channel, which can be a different type of channel. We'll talk about the different types in a minute. And we bring about some cellular response. Here, it's not so simple. We have a few players involved. And so we can do one of two things. We can generate some second messenger. So the binding of this neurotransmitter to this receptor, which is coupled to this G protein, turns on the protein. One of the subunits can activate this enzyme downstream in the membrane, and we can generate some type of second messenger, which will then bring about our cellular response, okay? Or we can have that subunit directly activate that channel, right? So we can have a second messenger do the activation, which is a bit more of a lengthy process, or we can have the G protein subunit directly coupled to that ion channel and bringing about a cellular response. So these are two options for our slow or metabotropic receptors. Okay, so let's sort of explain what exactly is happening at these receptors here. And this is going to call on stuff that we did already. We talked about graded potentials already, right? And we distinguished them from action potentials. And so basically when we have these ligand-gated channels, when they open on the membrane potential will do a different thing depending on what channel we opened, right? If we open up sodium or calcium channels, what type of event do you think will happen? If we open up a sodium or calcium channel, we're going to depolarize. I'm hearing depolarization, that's correct. So we have sodium and calcium. Sodium is going to want to go into the cell, so is calcium, they're positively charged. And so this is going to excite the membrane potential, and so we call it an excitatory postsynaptic potential, or an EPSP, okay? And so all this EPSP means is that we are depolarizing the membrane, we are increasing the membrane potential, it's becoming more positive. And opening up of channels like sodium channels or calcium channels can facilitate this positive change in the membrane potential, right? Alternatively, we have chloride and potassium channels. And opening of these channels result in a hyperpolarizing event. And so we know hyperpolarization is moving away from, or more negative from our resting membrane potential, right? Think about becoming -80, -90, closer to potassium's equilibrium potential. And so when we open up a potassium channel, although potassium is positively charged, we really want to understand here, and we should at this point, that the ECDF for potassium is outside of the cell. Okay, and so if you open up a potassium channel, the forces acting on potassium will drive it out of the cell. And so that will result in hyperpolarization. Okay, so not because this is a positively charged, remember the direction that this ion is moving in. And that's called an inhibitory postsynaptic potential, or an IPSP. And we can also bring this about opening a chloride channel. We haven't spoken about chloride very much, and chloride is very unique in its effect on the resting membrane potential. But chloride will rush into the cell, and being a negatively charged ion, it will also hyperpolarize the membrane, sorry. It will hyperpolarize the membrane because it's going to make it more negative, being a negatively charged ion. Okay, chloride also has this very unique function in that it can reestablish or stabilize the resting membrane potential. And I'll talk a little bit about how that's done. So potassium and chloride can bring about IPSPs, and then chloride specifically can also help with stabilizing the membrane potential. Okay, so to really sort of explain here again, or reiterate here, EPSPs are common at synapses where we have glutamate, right? Glutamate is going to be excitatory, and that's an example of an excitatory neurotransmitter because it's going to open up what type of channels do we think? If it's generating an EPSP, what type of channels? Sodium or calcium, exactly. So if we think about glutamate being the neurotransmitter, bringing about an excitatory postsynaptic potential, it will likely open up sodium or calcium channels. On the other hand, GABA, which is inhibitory, it's going to bring about an IPSP, will likely open up what type of channels? potassium or chloride. Exactly, potassium or chloride. And you want to remember here that those ions are flowing in different directions. So chloride going in hyperpolarizes the membrane, potassium moving out also hyperpolarizes the membrane. Okay, and so these are just two examples of some neurotransmitters, glutamate being excitatory, GABA being inhibitory. And these are amino acids in terms of their makeup. Okay. All right, so let's look at differentiating these some more. So an excitatory postsynaptic potential will definitely or more likely produce an action potential. And this is because it is depolarizing the membrane, right? Whereas an inhibitory postsynaptic potential will not be leading us to an action potential. It's moving further away from that threshold. And so it's going to hyperpolarize the membrane, one, but also it has this ability to stabilize the membrane potential, right? And I sort of pointed that out, specifically chloride. The movement of chloride in specifically stabilizes the membrane potential. So just sort of to reiterate that here, EPSPs will generate an action potential or will be more likely to, right? They're heading towards threshold. Whereas IPSPs are less likely to produce an action potential. They're moving further away and they can either hyperpolarize the membrane or stabilize the membrane potential. Okay, so this is just comparing that fast and slow response, which we talked about. And here I just want to point out that depending on what type of channel we open, so let's say this was a membrane on a second neuron, a postsynaptic neuron, and we opened up a sodium channel, right? By binding of that neurotransmitter to this receptor. So the receptor is also acting as a channel. And so the movement of these ions is what then brings about the cellular response. And can we see how that can be very fast, right? Immediate almost. The binding of this neurotransmitter opens up that channel, cellular response, okay? Whereas metabotropic, we said, this is not that simple. The receptor is coupled to another middleman, as I like to call them, which is this G protein, and then it's going to dissociate and it's going to send a message to another enzyme. And so there are some players involved here, and this is going to take time. And the important take-home point here is that we must generate either a second messenger to bring about our cellular response, or the subunit of this G protein must directly couple to that channel and open it. Okay, so it's really important for you to sort of summarize the differences on this slide so that you don't get these confused on questions. All right, let's talk some more in detail about the inhibitory synapse. Okay, so we said the movement of two ions brought about IPSPs, and those could be chloride or potassium. Now, potassium is pretty straightforward. We know that if it moves out of the cell, it will leave that unopposed negative charge inside the cell. The inside of the cell becomes more negative. That will be a hyperpolarizing event. Chloride now becomes a little bit more interesting. Chloride can do two things. So it can bring about an IPSP on a neuron, okay? So on a neuron, it will bring about an IPSP, and I'll talk about the mechanism here in a minute. But then on a non-neuron, on a non-excitable cell, it will stabilize the membrane potential, okay? So let's sort of talk about what that means. So we know that this is an example of a neuron, and on neurons, there's an active pump that's pumping chloride out of the cell. And so pumping chloride out of the cell creates a concentration gradient where chloride wants to move back into the cell, okay? And so the movement of chloride back into the cell here is what generates this IPSP, okay? Very straightforward. So this flow where chloride passively moves along its gradient, as long as this channel is open, remember that's the context that we're talking about this, right? A neurotransmitter binds to this channel, and if it's open, chloride has a gradient. It has a passive gradient now, it's gonna flow right into the cell. That's an IPSP. On a cell that does not have this active pump, right? So this is a non-excitable cell. This does not have this structure. It doesn't have the active pumping of chloride out of the membrane. So this is not a neuron, not an excitable cell, no active pumping of chloride. We have the leaking of chloride. So chloride is freely leaking across the membrane, and now it's at equilibrium. Okay, so it's moving freely in either direction, not being accumulated on either side, and so we have chloride moving at equilibrium. So on this very same cell, right, this is the same cell here, let's look at two synapses on the same cell where we have chloride moving at equilibrium. So we have an excitatory synapse. This is two different synapses where we have neurotransmitter 2, and then we have an inhibitory synapse where we have neurotransmitter 1. So these neurotransmitters are opening up chloride and a sodium channel respectively, right? So just to review here, this would be an EPSP, this would be an IPSP. But on this cell, this would not act as an IPSP because in this way, this receptor is simply negating the action of the sodium receptor, okay, the sodium channel. So for every positive charge that comes into the cell, chloride wants to get back to equilibrium. And if we introduce unopposed positive charge inside the cell, that tips that balance off. And so one chloride is basically pulled into the cell to counteract that positive charge. So for every sodium that comes into the cell, one chloride comes into the cell. And what does that do to the membrane potential? Will it depolarize it, will it hyperpolarize it, or will it keep it steady? If for every sodium we bring into the cell, we bring in a chloride, what will that do to our membrane potential? It will stabilize it. It will keep it nice and steady. And so in this way, having a chloride channel here on a non-excitable cell that's not actively pumping chloride out stabilizes the resting membrane potential or stabilizes the membrane potential. Okay, so we make it very hard to depolarize this cell. And in some instances, that is what we want. That is the effect that we want or the desired outcome. So just to drive home again here, we have this nice, easy, an IPSP, which is where we're hyperpolarizing the membrane. Okay, make sure we make that distinction. Here we're hyperpolarizing the membrane. And so we're making it more negative inside the cell. On this cell, which is not a neuron, we're not hyperpolarizing the membrane. All we're doing is negating any sort of depolarizing events. All right, so we're just keeping the membrane potential stabilized in this way. Okay, so let's look at a little bit of an example here of how these IPSPs or graded potentials are transmitted. So we spoke about action potentials, we spoke about the difference in frequency of action potentials, and we pretty much said that we cannot grade an action potential, right? They all look exactly identical, but in order to appreciate or to signal varying degrees of a stimulus, right? Let's say we perceive a loud sound as opposed to a medium sound, as opposed to a quiet sound. Let's say we perceive a hot stimulus or a very painful stimulus versus a not so painful stimulus, right? The nervous system has to be able to grade these things, right? And so the way that we grade action potentials is playing around with the frequency. We talked about that before. So a higher frequency of action potential generates or translates rather to more neurotransmitter. Higher frequency of action potentials, which can be signaled by a supra-threshold stimulus. So we talked about these different types of stimuli, a supra-threshold stimulus versus a sub-threshold stimulus. And if we get a supra-threshold stimulus, we generate more action potentials, right? Faster, a faster frequency or higher frequency, which translates to more neurotransmitter, which translates to more receptors being bound. And if we have more receptors being bound, we open up more channels, which facilitates more ionic movement. And then we have a greater or lesser movement of the ions, okay? So basically, we can use this frequency of the action potential, how fast we're firing them, to sort of degree or to grade, right? Or to code the strength of the signal. And so we can have a stronger influx of ions giving us a stronger signal, or a less influx of ions or slower influx of ions giving us a weaker signal, okay? So don't think that because action potentials are not graded, that they're all or none, that we cannot grade different stimuli, right? We can have subthreshold stimulus, threshold, and